Hi, all. Welcome back to discussion on foundations of quantum mechanics. So today we are going to discuss one of the simplest topic in quantum physics or quantum mechanics called free particle. Now, first we have to answer what is meant by free. Okay, we already discussed this free particle. You might be knowing about this free particle in classical physics itself. The term free represent it is force free. There is no the force on the particle. There is no net external force on the particle. Or in other words, there is no interaction on this particle. So the free means the force is zero. So in classical physics, the free particle means the force is zero or the potential is zero. So if the potential is zero, then using the second law of thermodynamics, we can write dp by dt equal to zero, or momentum will remain a constant, or the ratio between v by m would be a constant. And now m is the mass of the particle. It is again another constant. So v can be written as a constant into constant, that will become another constant. So finally, in classical physics, the free particle is something which is having a constant velocity, or we can call it is in the uniform motion. And that is about the first law of motion, the first law of the Newton's first law of motion. That is, until unless the particle is experienced unbalanced external force, the particle will remain in the uniform motion. So if the force is zero, the velocity remains constant or the particle will be in uniform motion. Now, how we'll describe or how we'll study the free particle in case of quantum physics or quantum mechanics. Now, in quantum mechanics, the approach is entirely different. We cannot use the Newton's law. So instead, we have to use the Schrodinger equation. And what we'll be finding is the wave function. So in free particle in quantum mechanics, we have to solve the Schrodinger equation and find psi of xt. So we have to use the time dependence on the equation, and we have to find psi of xt. Now we have one easy way to do this. So instead of directly solving the time dependence on the equation, first we can solve the time independence on the equation, because in case of free particle, the potential is always zero. So if the potential is independent on time, then we can solve the time independence on the equation and find psi of x. The psi of x is called the stationary state. Okay, there's the solutions of time independence from the equation is usually called the stationary state. So once you find the stationary state, then we can write the total wave function as a product of the psi of x and e raised to minus iet by h cross. So all these details we have discussed in the previous lectures. So those who are not want to read, please go through those lectures to understand how we can write this expression. Now the time independence from the equation we can write in this form: minus h cross square by 2m, the second derivative of psi, plus v psi, since v is 0, so this term will become 0, equal to E into psi, where E stands for the energy of the particle. Now solving this is very trivial thing. So we have d square psi by dx square equal to minus 2me by h cross psi of x. And now I am going to denote this 2me by h cross square as k square, so that my differential equation can be written as d square psi by dx square is equal to minus k square psi. Now, this is a very simple differential equation. We have already seen this kind of differential equation in the particle in infinity deep well. So the free particle in infinity deep well, we have gone through the similar equation. So here the case is, if you find the derivative, if you find the second derivative of psi, we are getting the psi itself with a multiplication factor minus k square. So the possible solutions are sine kx or cos kx, or instead we are going to use the exponential form of the solution, e raised to ikx and e raised to minus ikx. So these are the two possible solutions. So it is also possible to write sine kx cos kx form, but in this particular case, I prefer this exponential representation, because that will be very handy to use. So we'll see that why I have used this exponential representation instead of sine form later. Okay, so therefore the psi k of x. So the here this is the the stationary solution, the stationary state, the psi of x. So I have used a subscript k here and index k here in order to show that it is for a particular k, because the free particle can acquire different energy. So for different energy corresponding to different energy, we can have different k values. So obviously we can have different psi. So for one particular energy, the the k value will be fixed, and the corresponding wave function I denote by symbol psi k of x. So this is for a definite k. For a different k, the wave function is of the same form. Only thing is we have to change the value of k in this case. So it is a superposition of e raised to I kx and e raised to minus kx, and I have introduced two constants a and b. Now the solution of the time dependence from the equation would be the stationary solution multiplied by this phase factor. This phase factor usually called the dynamic phase factor, e raised to minus iat by h cross. Okay. So if you multiply this psi k of x and e raised to minus iat by h cross, I can write it is a into e raised to I kx minus at by h cross plus b into e raised to minus I kx plus at by h cross. Now we have already found the form for e in terms of k. So e is h cross square k square by 2m. So if you substitute it here, one h cross will cancel. So it would be h cross k by 2m. Not here, I have taken a k commonly outside, so it is h cross. Actually, it is h cross k square by 2m, but since I have taken k commonly outside, it is h cross k by 2m. So we have the first term a into e raised to I k times x minus h cross k by 2m into t plus b. The only difference here is the sign of x and the time factor are same. So you might have seen this kind of the function when you have studied your the UG level course on wave. So these functions represent progressive wave. So any function, remember, any function is of the form x plus vt or x minus vt represent a progressive wave. So x plus vt wave represent the wave propagating in negative x direction, and this is the wave propagating in positive x direction. The reason is if you look at this wave, so any kind of wave is of the form of x minus vt. So suppose consider a point on the wave. So this point on the wave will have a fixed value for x minus vt. Suppose this x minus vt equal to some alpha. Now, what will happen when time increases? So the point with the same alpha will be look like the same shape. So after the later time, in order to make x minus vt constant, so x must increase. So when t increases, x must also increase in order to make alpha same. Okay, so the wave with x minus vt or the point with x minus vt constant will move forward when time increases. Okay, so if we need the further clarification on this progressive wave, I have already made a video lecture on the discussion about the propagation of wave. I will give the description in the comment box, so you can go and watch it. Okay, so these two waves represent a propagating, both are propagating wave, progressive wave. One is along the positive x direction, and another is along the negative x direction. Okay, so the first one is propagating in positive x direction, and the second one propagating in negative x direction. Now this term is the speed, because remember this f of x plus vt, the v stands for the speed of the wave, or in x minus vt again v stands for the speed of the wave. So here instead of v, we are getting h cross k by 2m. So that means the speed of the wave is h cross k by 2m. So that is what I have written here. So psi k of xt represent two progressive wave. The first represent wave propagating in positive x direction, which is speed h cross k by 2m, and the second term represents the wave propagating along negative x direction with the same speed h cross k by 2m. So the speed of the wave is h cross k by 2m. Okay. Now it is possible to write this expression. This expression instead of the two term, I can write with a single term. And the only thing is we have to allow the k to be negative. So if k is positive, it represents the wave propagating in positive x direction. And if k is negative, it represents the wave is propagating in the negative x direction. So this gives a complex representation of psi k of xt. Okay, so this kind of, so I have combined two different solution into one single form. So this is the beauty of this exponential form of the function. So instead, if you use the sine and cos, I have to always represent the two different function. Both sine and cos has to be represented to represent psi k of xt. Now it is possible to, since I have used the exponential representation, now it become very easy to represent psi k of xt in a single term. And only in the additional condition I have used is k can take a negative value as well. So here in the previous case, here k is always positive, but here the k can also take negative. Okay. Now, if you we can compare the wave velocity with the particle velocity. So we have found that the velocity of wave is h cross k by 2m. Now, h cross k is nothing but momentum. So how you found the h cross k is equal to momentum? So we can show this one some simple steps. So remember E is h cross square k square by 2m. Okay, so this expression we have already written earlier. Now, here the particle is free. So, for free particle, the total energy would be simply kinetic energy. So, it is simply equal to half mv square. So, we can write half mv square equal to h cross square k square by 2m. Or half mv square we can also write as p square by 2m if you want. Or h cross square k square by 2m we can write as p square by 2m. Or this implies, so if you look at this expression, p square and h cross k square are same, or p is equal to h cross k. Okay, so h cross k can be written as p by 2m, or p by m is v, the velocity of particles, so v by 2, or the velocity of wave become the velocity of particle divided by 2. So that means we are getting the velocity of wave, which representing the free particle, as a velocity less than the particle velocity. So how that is possible? Okay, recall in quantum mechanics, the particle can also be represented as a wave. So if the particle is moving with some velocity, and if the wave is moving with the lesser velocity, so will that represent uh, the wave component is, will that represent that matter wave or not? So obviously, if some wave represent the matter wave, so it must have the velocity of the particle. But here we are getting different velocity. So is it an acceptable solution? Is psi k of xt of the above form is acceptable solution? Okay, so just pause it and think about it. Now I will give one more issue here. Now if you look at the psi k of xt directly, if you integrate the psi k of, if you integrate mod psi k of x square, what would happen? Okay, so look at here. Okay, so the another problem is the psi k of x is not normalizable. That is, if you integrate mod psi k of x square from minus infinity to plus infinity, what will you get? If you integrate this, it will be mod a square. The mod square of this term is 1. So it is simply mod a square dx. And mod a square is just a constant. Just take it outside and integrate dx from minus infinity to plus infinity. And obviously, that will give you infinite value. So that means the psi k of xt is of above form is not normalizable, and the velocity of this wave is not equal to the velocity of the particle. So in this both these circumstances, the psi k of xt is not an acceptable solution. Remember, the psycho of xt is the harmonic form. It is a harmonic wave. So this harmonic solution is not a possible solution. So then how we can represent the wave function for the free particle? Remember, the free particle exists. Okay, so if the particle is not experiencing any kind of force, it is free. So free particle must be represented by some wave function. So, but it cannot be represented in this form. So what is a possible solution? Recall is we know that if you have various solutions, because remember the cycle of xt is not a single solution. There can be many possible k values. So therefore, the superposition of psi k is another possible solution. So if you define a psi of xt, which is of the form 1 by root 2 pi minus infinity plus infinity phi of k psi k of xt dt. So if you define a psi of xt, a new wave function in this form, now it is possible to normalize the psi of xt. That means it is possible to write the psi of xt as it is possible to take the psi of xt as the wave function for the free particle. Now it is no need to worry about this expression. This expression is simply the generalization of our previous expression, because we know that if once you find psi k of xt, the general solution is simply sum over k ck psi k of xt, where ck is called the expansion coefficient. So this is familiar to us. We can always write the wave function as a superposition of the basis function. So psi k of xt, the different values of k, all are the possible solutions of the Schrodinger equation. So its superposition is again a possible solution. Now here in this particular problem, instead of taking summation, we have taken the integration, because the k can take all possible value from minus infinity to plus infinity. There is no restriction, there is no discreteness. It is the k is now is a continuous variable. So instead of a discrete summation, it must be a continuous summation. So that is why we have taken the integration. And obviously, we have introduced some constant 1 by root 2 pi, that is for some purposes that we'll see later. Okay, so right now we cannot tell what is the use of this 1 by root 2 pi. Okay, so right now there is some constant 1 by root 2 pi. Now we are saying that we are, so I am arguing that the psi of xt is now normalizable. Remember, psi of xt is our the solution that we have got earlier, but the psi of xt is not an acceptable solution. But the superposition of psi of xt, which is of the form this, is an acceptable solution. Okay, now the psi of xt contains many harmonic functions. Okay, so this is a superposition of many psi k. So there can be psi k1, psi k2, psi k3, etc. So the psi of xt contains many harmonic functions. So therefore, the psi of xt is usually called a wave packet. Okay, so it contains many harmonic functions with a different k, with various k, and hence it is called a wave packet. So this new function is a wave packet. So it is look like this. So a single function like this cannot be represent a free particle. But if we have the superposition of, so if you have superposition of many harmonic functions, okay, all these must be superpositions. If you add many of these, you may get the wave function might like this. This kind of wave function is possible. So this is a superposition of many waves. So this wave is called wave packet, and these are individual harmonic wave. So individual harmonic wave is not a possible solution. That is not acceptable. It is not acceptable. Okay, I will use some other color. So this is not acceptable, but this is acceptable. The wave packet is acceptable. The sum of all are acceptable. Individually is not acceptable. Okay, I think you have understood what I'm meaning. Okay, so remember this psi k of xt is contains a harmonic wave, and that is not an acceptable solution. Whereas the superposition of many harmonic wave is is a possible solution. Actually what happens is if you took a single wave, then its mod square will go to infinity, or sum of mod square will go to infinity. But if you add many wave functions, many harmonic functions, then it is possible that it in superposition there can be some kind of destructive interference, and the wave function must be vanishing for very large x. So that might be possible for some kind of superpositions. Okay, so only certain superpositions would be valid, not all these integration would be valid. Only certain superpositions would be valid. Only the main thing is the psi of xt, the new psi of xt must be normalizable. Okay, so our conclusion is we can conclude that the free particle wave function cannot be represented by a single harmonic wave. Okay, so the free particle wave function cannot be represented by a single harmonic wave. It must be represented as a superposition of many harmonic waves, and it is called the wave packet. Okay, now in the case of wave packet, we have seen a constant. So instead of ck, the expansion coefficient, we have seen phi of k. Now our next aim is to find what is phi of k. Now we know that psi of xt can be 1 by root 2 pi raised to x integral minus integral plus infinity phi of k psi k of xt dk. So just substitute the form of psi k of xt. So psi k of xt contains some constant a, into e raised to I k x minus h cross k square by 2m into t into dk. So this is my psi of xt. Now what I am doing is I am going to absorb this a into phi of k, and therefore hereafter I will not write a here. The wave function is simply phi of k, is simply this phi of k into e raised to I kx minus h cross k square by 2m into t dk. Okay, so there is some a, but that a I have included in phi of k. So that is should possible because this I have not defined this phi of k right now. So I have absorbed this phi of k. So my new phi of k contains that a also. Okay, so there is no problem of writing the psi of xt of this form. Okay, so there is no need to worry about a. The a is absorbed in phi of k. So therefore the psi of xt I have written in this elegant form. Now, what would be the wave function at time 0? So the phi of k we can find if we know that condition. So that is called initial condition. So psi of x0, so psi of x0 we can write 1 by root 2 pi minus inverse plus infinity phi of k, it simply become e raised to I kx, so its entire term will become e raised to I kx into dk. Okay, so this is a kind of inverse Fourier transformation. So therefore, this phi of k is the Fourier transform of psi of x0. So using this theorem, the Fourier transformation of the phi of k can be written as 1 by root 2 pi integral psi of x0 e raised to minus I kx dx. So this is called the Plancher's theorem. So that we can, in general, we can write like this. Suppose you have some function f of x, so f of x equal to 1 by root 2 pi integral minus infinity to plus infinity capital f of k e raised to I k x dk. Then f of k would be 1 by root 2 pi minus infinity to plus infinity f of x a raised to minus psi kx dx. So this f of k is called Fourier transform of small f of x. So this capital F of k is a Fourier transform of small f of x. So similarly, this phi of k can be identified as Fourier transform of psi of x0. So therefore, phi of k we can find by using the initial condition. Phi of k is 1 by root 2 pi minus plus infinity psi of x0 e raised to minus I kx dx. Okay, now finally we can, so in this way we have solved the problem of normalization. So if you introduce the total wave function as a superposition of as the integral as a superposition of the psi k of x, it is possible to find a normalized psi. So that is called the wave packet. Okay, and the corresponding coefficient phi of k we can find from the Fourier transform condition. Finally, we have to check what would be the speed of this psi of xt, the wave packet. What is the speed of this wave packet or the velocity of the wave packet? So it's usually called the group velocity. So we can find that. So we know that psi of xt again we can write as 1 by root 2 pi minus plus infinity phi of k e raised to I kx minus h cross k square by 2m into t dk. Now I'm going to introduce a new quantity called omega. So omega I have denoted as for h cross k square by 2m. So therefore psi of xt can be written as 1 by root 2 pi minus infinity pi of k raised to I kx minus omega dtk. So this is a familiar form e raised to I kx minus omega t. E raised to I kx minus omega t represent a progressive wave which is moving in the positive direction. It is positive. And moreover, it has velocity v is equal to omega by k. So for a particular k, k e raised to I k x minus omega t basically represent wave is moving along x direction and its speed. So that speed we can call it the phase velocity would be omega by k. So the phase velocity would be omega by k. And what is that omega by k? It is h cross k by 2m. But that is the half of particle velocity. Okay. So the phase velocity is again omega by k, which is half of the particle velocity. But if you look at, but we are not interested in the phase velocity of this wave packet. We are interested in the group velocity. Okay. So in order to find the group velocity, what I have to do is I have to expand this omega about some k value. So fix some k value as k0. So we can expand omega of k about some point k equal to k0 in Taylor expansion, Taylor series. So omega of k can be written as omega at k0 plus k minus k0 d omega by dk at k0 plus etc. So I'm going to denote this omega at k0 as omega 0 and d omega by dk at k0 as omega 0 prime plus etc. Now, where the value is very near to k0, for k near to k0, so this wave function psi of xt can be 1 by root 2 pi minus into the infinity phi of k e raised to, instead of this kx minus omega t, I am going to replace this omega with this term. So I am going to take only the first power of k minus k0 because k is very near to k0. So the higher orders of k minus k0 would be negligible. So I have taken only up to the linear term of k minus k0. So in that way, I can expand the second term omega by using omega as omega 0 plus k minus k0 omega 0 dash. Okay, so after that, I'm just going to rearrange the term. So here we have a kx term here, and we have an omega 0 prime t here. So I'm combining those two terms first. So e raised to I k x minus omega 0 prime t minus we have an omega 0 t here and we have k0 omega 0 prime t that I have written in the second part. Okay, so if you just take it into inside the integration, but this term are not function of k. So this can be taken outside. So this can be written as e raised to minus I omega 0 t minus k 0 omega 0 prime t divided by root 2 pi. And we have this factor. Or again, if you look at this e raised to minus I, so this factor has common time t is common, can be taken outside 1 by root 2 pi minus t plus infinity phi of k raised to I k x minus omega 0 prime t dk. Okay, so if you look at this expression, so this is a kind of phase factor. But if you look at here, it has x minus omega 0 prime t factor. Now recall our earlier discussion. So any function is of the form x minus vt or x plus vt represent progressive wave with a speed v. So the factor which comes with t is the speed. Okay, so here also, if you look at this expression, it is a function of. So this is a function of, we can write, it is a function of, instead of f, so it is a function of x minus omega 0 prime t. So therefore, what would the speed of this wave? The speed of the wave would be omega 0 prime. So that means the wave packet psi of xt must be propagating the speed omega 0 prime. And what is omega 0 prime? D omega by dk at k equal to k0. Or simply we can say that d omega by dk will be the speed of the wave group or the wave packet, and it is called the group velocity. Okay, so d omega by dk is called is the velocity of wave group, or more correctly we can write the wave packet, and it is called the group velocity. So when you have found the expression for the group velocity, so there is the group velocity of the wave, which is d omega by dk. This is d by dk. What is omega? H cross k square by 2m. And if you do this, you can get h cross k by m, and h cross k is momentum, so it's momentum by mass will give the velocity of the particle. Okay, so this is a remarkable thing. So here we have found the group velocity is the group velocity of the wave packet is same as the velocity of particle. Okay, so that means we have getting the particle velocity is same as the velocity of group wave, the wave packet, and as well as this wave packet, the wave function in the form of the wave packet is a normalizable. So therefore, the free particle, the wave function of the free particle has to be written as a superposition of the harmonic wave, or instead we can say that the wave function of the wave particle must be a wave packet. It cannot be a single harmonic wave. It must be a wave packet. Okay, so that's all about the discussion about the free particles. I will just summarize what we have discussed till now. Okay, so the free particle, V of x is 0, and the solution psi k of xt is of the form a raised to I kx minus h cross k square to m into t is not acceptable solution. There are two reasons. One is the velocity of the wave is not matching with velocity of particle, and another one is the psi of xt is not normalizable. Okay, but there is a way out for this problem, and what's the way out? Define the superposition of this psi k of xt. So psi of xt is 1 by root 2 pi minus infinity to plus infinity phi of k psi k of xt dk. So if you define the psi of xt, so the psi of xt is called the wave packet. Why it is wave packet? Because it is a superposition of many harmonic wave. Remember, the psi k of xt is simply a harmonic wave, or this can be written as 1 by root 2 pi integral minus infinity to plus infinity phi of k e raised to I kx minus equals k square by 2mt into dk. Okay, I have included this a, the constant a, inside this phi of k. So this is normalizable for certain. It is not. It is not normalizable always. So for certain phi of k, it is normalizable, and the speed, velocity of this wave packet equal to the velocity of particle. And the velocity of wave packet is the groove wave, which is d omega by dk. It is same as velocity of particle. So that means the expression that we have found out in this form is an acceptable solution. So this is the solution for wave particle. Okay, so thanks for watching this video. So keep watching this video and put your comments in the comment boxes. So that will give a good feedback for me for making the other videos uh, with in more efficient way. So thank you once again. So see you soon. Bye.